All right, let's dive into a chemical mystery that, and I'm not exaggerating here, has literally been a matter of life and death in the world of medicine. I mean, how can the exact same medicine be both a cure and a poison? It sounds like something out of a movie, right? But this is a very real puzzle that had scientists scratching their heads for a long time. So, what's the secret? Well, let's get into it. So, to really understand this, we've got to start with the evidence. And believe me, some of these cases are pretty shocking. Okay, just look at these examples. You've got naproxen, right? One version is a lifesaver for people with arthritis pain. Its identical twin, it can cause serious liver damage. Then there was a tuberculosis drug. One form worked, the other could actually cause blindness. And of course, the most famous and tragic case, thalidomide. One version helped with morning sickness, but its mirror image, well, it caused horrific birth defects. And the crazy part is, these aren't different chemicals. They are made of the exact same atoms. So what on earth is going on here? The whole secret, the key to this entire mystery, comes down to the molecule's three-dimensional shape. It's all about one tiny but incredibly important detail. And here it is. Meet our main character, or maybe our villain. It's called the chiral carbon. Now, it's just a regular carbon atom, but with one special rule. It has to be bonded to four completely different groups. That one little detail, that's what unlocks this whole mirror image world. So because of that special carbon, the molecule can exist in two versions that are perfect mirror images of each other. The classic example is, your own two hands. Hold them up. They're mirror images, right? But try to lay your right hand perfectly flat on top of your left hand. It doesn't work. They're non-superimposable, and that's exactly what these molecules are like. In the chemistry world, we call these special twins enantiomers. Now, this is where things get really, really weird. If you have these two enantiomers in a beaker, they seem totally identical. Same boiling point, same color, same density, you name it. You can't tell them apart. But the moment they get inside your body, it's a completely different story. They go from being identical twins to fraternal twins with wildly different personalities. So that's the big question, right? If they're identical in almost every way, how in the world do you separate the good twin from the bad twin? Well, scientists came up with a really clever trick, and it all has to do with light. Okay, here's how it works. Think of normal light from a light bulb. The waves are vibrating all over the place, up, down, sideways. The first step is to pass that light through a filter, kind of like the lens on polarized sunglasses. That filter lines up all the light waves, so they're only vibrating in one direction, or one plane. Then you take that neat, orderly light and shine it through a tube with your chemical sample. And this is where the magic happens. The molecules actually grab that plane of light and give it a twist. And here's the clincher. One of the twins will always rotate the light clockwise, to the right. And its mirror image? It rotates the light anti-clockwise, to the left, by the exact same amount. It's like their own secret handshake, a unique optical fingerprint that finally lets us tell them apart. Okay, so what if you mix them together? A perfect 50-50 split of the left twisting and right twisting molecules. Well, chemists call this a racemic mixture. And what happens is, for every little twist to the right, there's an equal and opposite twist to the left. They completely cancel each other out. The light goes in straight and it comes out straight. The mixture is what we call optically inactive. You can see it right here. If your mix is, say, 80-20, you're going to see a big net rotation. But that perfect 50-50 racemic mix, absolutely zero rotation. And this was the huge problem. For years, the standard way of making drugs produced these 50-50 mixtures. You were getting half cure and half poison, all mixed together. All right, so we figured out how to tell these twins apart in the lab using light. That's great, but it still doesn't answer the most important question. Why does our body care so much? Why does it treat them so differently? And the answer, it turns out, is amazing. The reason our bodies can distinguish between these mirror image molecules is because our bodies are also built out of mirror image molecules. Our own enzymes, our proteins, even our DNA. They are all chiral. They have a specific handedness. Honestly, the best way to think about it is the glove analogy. Imagine an enzyme in your body is a right-handed glove. The helpful drug molecule is your right hand. It slides in perfectly, a snug fit, and it can do its job. Now try to put your left hand into that right-handed glove. You can kind of jam it in there, but it's not right, is it? It doesn't fit. It either does nothing at all, Or worse, it gets stuck and causes a whole new set of problems. So at the end of the day, it's all about shape. It's a classic lock and key situation. Our enzymes have these incredibly specific 3D pockets called active sites. Only one of the mirror image molecules, the right hand, has the perfect shape to fit into that pocket and kick off the chemical reaction we want. The other one is just the wrong key for the lock. Once scientists figured this out, this whole chiral locksmith idea, it changed everything for the drug industry. I mean, it was a total game changer. Now they knew the problem, and they could finally start engineering a real solution. And the mission became simple, really. Stop making these messy 50-50 mixtures. The new goal for drug companies was to figure out how to make only the one single effective enantiomer. That way, you know that every single molecule in that pill is the good stuff. And check out the difference this makes. It's huge. The old way gave you that 50-50 mix. That means half your dose was useless or even harmful, so you needed to take more, which increased the risk of side effects. But with the new methods, you get 100% pure product. The dosage can be cut in half, the risk of side effects plummets, and the drug itself is way more potent. So how do they pull this off? Well, there are two main tricks. They can use these amazing man-made things called chiral catalysts. Think of them as tiny molecular shepherds that guide the reaction to make only the left-handed version or only the right-handed one. Or, and this is really cool, they can just borrow from nature and use enzymes themselves. After all, enzymes are nature's perfect chiral catalysts, and using them is often a much greener way to do things. So there you have it. The mystery of how one medicine can be both a cure and a poison is solved. But it kind of leaves you with a much bigger question, doesn't it? If our bodies are built on this principle of handedness, what other invisible, mirror image molecules are out there influencing us? Not just in our pills, but in the food we eat, the air we breathe, shaping our world in ways we're just beginning to understand. It really makes you think. Sometimes the most profound differences are hiding in a simple reflection.